Let's discuss infinite limits. This lesson will help you determine infinite limits from the left and from the right. And this will also help you find and sketch the vertical asymptotes of the graph of a function. Now consider the function f of x equal to 3 over x minus 2. This figure here shows the graph of the function f of x equal to x over x minus 2. While this table here shows the values of the function as x approaches 2 from the left and from the right. As you could see here from the graph, as x approaches 2 from the left, f of x decreases without bound. While if as x approaches 2 from the right, f of x increases without bound. And that can also be confirmed by the values here in the table. As you approach 2, you notice from x equals 1.5, it is just equal to -6. If you have x equals 1.9, you have -30. And then if you go closer and closer to 2, like 1.99, you have -300. And see, if you have 1.999, you then have -3000. So if you notice, the values of f of x decreases dramatically. And also, if you look at the values of x as x approaches 2 from the right, x also, the y value or the function, y value function or the function of x also increases dramatically. This behavior is denoted by this. So for f of x decreases without bound as x approaches 2 from the left, we say that the limit of the function 3 over x minus 2 as x approaches 2 from the left is equal to -infinity. And also we notice that f increases without bound as x approaches 2 from the right. Therefore, we say that the limit of the function 3 over x minus 2 as x approaches 2 from the right is equal to +infinity. Now, these symbols do not represent real numbers. They are just convenient symbols used to describe unbounded conditions more concisely. A limit in which function f of x increases or decreases without bound as x approaches c is called an infinite limit. For instance, in here, both the function from as x approaches c from the right or from the left, the behavior increases or the function increases without bound. That's why we say that the limit of the function as x approaches c is equal to +infinity. So the formal definition of infinite limits is given by this theorem here. Let f be a function that is defined at every real number in some open interval containing c except possibly at c itself. This statement, the limit of f of x as x approaches c is equal to infinity, means that for each m greater than 0, there exists a delta greater than 0 such that the function f of x is greater than m whenever x minus c, absolute value of x minus c, is less than delta. You can verify that from this, you can verify the definition from this figure here. And similarly, this statement, the limit of f of x as x approaches c equals to -infinity, means that for each n less than 0, there exists a delta greater than 0 such that f of x is less than n whenever this absolute value expression is less than delta. Now let's consider the following graphs here and determine the limit of each function as x approaches 1 from the left and from the right. For the first graph, as x approaches 1 from the left, the function or the graph increases without bound. So the limit of the function as x approaches 1 from the left is equal to positive infinity. Similarly, as x approaches 1 from the right, the limit of the function is also equal to positive infinity. It also increases without bound. And in here, the limit of the function as x approaches 1 from the left is positive infinity, while the limit as x approaches 1 from the right, the limit of the function as x approaches 1 from the right is negative infinity. Although in this case, they do not have the same limit, left-hand limit and right-hand limit, we can tell by looking at the graph that both of these functions has an asymptote at x equals 1. Now let's try to compute the limit analytically. Now when x approaches 1 from the left or right, this expression here is a small positive number. So if we have 1, when you say 1 from the left, that is actually a value that is less than 1. Let's say, for instance, 0.99. So 0.99 minus 1 is 0.01, and then you square that. So that's a small positive number. It will always be positive because of the square sign here. Similarly, if I have a value of x from the right, say 1.1, 1.1 minus 1 is 0.1, and you square that, it's still a small number that is positive. Now, the quotient, if you have a very small number and you get the reciprocal, so the quotient, that is 1 over x minus 1 squared, that is the reciprocal of this, is a large positive number, and it approaches infinity from each side of x equals 1. So therefore, we can conclude that this is equal to infinity. So the limit as x approaches 1 of the function 1 over x minus 2 squared is equal to infinity. For letter B, as x approaches 1 from the left, this expression here is a small negative number. Now, the quotient, this quotient negative 1 over x minus 1 becomes a large positive number. And therefore, as f of x approaches to positive infinity from the left of x equals 1. So therefore, you can conclude that the limit of negative 1 over x minus 1 as x approaches negative 1 is equal to positive infinity. And this is the limit from the left side. Okay, so and when x approaches 1 from the right, this expression is a small positive number. Thus, the quotient negative of x minus 1 becomes a large negative number. So therefore, f of x approaches negative infinity from the right of x equals 1. So therefore, you can conclude that the limit of negative 1 over x minus 1 as x approaches 1 from the right is equal to negative infinity. We say that this is the limit from the right side of 1, and that is equal to negative infinity. And this confirms this analysis here. The figure here confirms this analysis here. As the function, as x approaches 1 from the right, the function decreases without bound. So that goes to negative infinity. While as x approaches 1 from the left, the function increases without bound. So therefore, the limit is positive infinity. Now let's try to connect this to vertical asymptotes. Now, if it were possible to extend the graphs in this figure here toward positive and negative infinity, you would see that each graph becomes arbitrarily close to the vertical line x equals 1. This line here is called the vertical asymptote of the graph of f. Each graph here has an asymptote. We call this asymptote. So when you say asymptote, that is the line wherein the graph of the function would just approach to. Now let's give a formal definition of vertical asymptote. If f of x approaches infinity or negative infinity as x approaches c from the right or the left, then the line x equals c is a vertical asymptote of the graph of f. In example 1, note that each of the functions is a quotient and the vertical asymptote occurs at the number at which the denominator is 0. And the numerator, of course, is not 0. Now, the next theorem generalizes this observation. So this next theorem here gives us the idea on how we could find the vertical asymptote of a rational function. So if we have a rational function of the form f of x over g of x, if these two functions f of x and g of x are continuous on an open interval containing c, and this f of x, it must not be 0 at x equals c, or f of c must not be 0, and well, this g of x is 0 at x equals c. And on the open interval containing c, the values of x except at c, your g of x must not be 0. If that's the case, then we say that the function has a vertical asymptote at x equals c. In other words, if you're given a rational expression or a rational function and you want to find the vertical asymptote, all you need to do is test if or find the values of x that will make your denominator 0. So equate this to 0, solve for x. And then when you solve for that x, you have to make sure that the numerator must not be 0 on those values of x. If that is true, then that x equals that constant, will be the vertical asymptote. For example here, if we are to find the vertical asymptote of this function here, all you need to do is equate the denominator to 0 and solve for x. If you equate this to 0, that means that x plus 1 is equal to 0, and solving for x, you get x minus 1. Now when x is equal to negative 1, when x is equal to negative 1, this numerator is still equal to 1. This is not 0. So therefore, we say that this function here has a vertical asymptote at x equals negative 1. And we can confirm our result by looking at the graph of the function. This is the graph of the given function. As you see here, at x equals negative 1, the function just approaches that vertical line. It will increase without bound as x approaches negative 1 from the right, and would decrease without bound as x approaches negative 1 from the left. Next example, let's find the vertical asymptote for the function h of x equal to x squared plus 1 over x squared minus 1. To find the vertical asymptote, we just have to get the zeros of the denominator. And to do that, we will just factor this expression here. The factors of x squared minus 1 are x minus 1 times x plus 1. And then we equate each factor to 0 and solve for x. If you equate this to 0, you have x equals positive 1. And if you equate this to 0 and you solve for x, you get x equals negative 1. Now, the next step is to check whether the numerator is 0 at these points here. Now, if x is equal to negative 1, you have negative 1 squared, that's equal to 1. So 1 plus 1 is 2. So therefore, numerator is non-zero. Therefore, this is a vertical asymptote. Now, when x is equal to positive 1, you plug it in, so you still have 2 in the numerator. Therefore, numerator is non-zero. So from the theorem, we say that at x equals -1 and positive 1, we have these two are vertical asymptotes. And you can confirm your result by looking at the graph of this function here. This is the graph of the function x squared plus 1 over x squared minus 1. And as you see here, as x approaches -1 from the left, the function increases without bound. And as x approaches -1 from the right, the function decreases without bound. Also, as x approaches positive 1 from the left, the function decreases without bound. And as x approaches 1 from the right, the function increases without bound. So x equals positive 1, and -1 are vertical asymptotes. So for the third function, we have h of x equal to cotangent x. To get the vertical asymptote, you just have to write cotangent x as cosine of x over sine of x. Now, to find the vertical asymptotes, we can apply theorem 1.14. That is to find all the values of x that will make the denominator equal to 0. And then make sure that those values of x will not make the numerator equal to 0. So if you equate sine of x equal to 0, the values of x that will make this 0 are the multiples of pi. So we have pi, and then 0, and then 2 pi, and -2 pi. Note that at these values of x, the numerator is non-zero. So therefore, at x equals n pi, where n is an integer, we have vertical asymptotes for cotangent of x. So this next theorem here gives us the properties of infinite limits. For instance, we have limit of f of x as x approaches c, and that is equal to positive infinity, while the limit of g of x as x approaches c is equal to L for some number L, for some finite number L. Now, the sum and difference, if this is infinity and this is a constant, then the limit of that expression is just equal to infinity. Now, if you have a product, one is infinity, the other one is constant, the answer is just infinity. And take note that this follows the rule of sign. So if I change this to negative infinity, the sign would also change. Okay, so this one is assumed to be positive infinity, and this is, for instance, L is negative. So therefore, positive infinity times negative becomes negative infinity. And also, if you have limit of g of x over f of x, where the limit of g of x is a constant and the limit of f of x is infinity, that is just equal to 0. The limit of the quotient is just equal to 0. Now let's look at some example to apply theorem 1.15. So the limit of 1 as x approaches 0 is just equal to 1. Limit of a constant is constant. Now the limit of 1 over x squared, so x squared as x approaches 0, this is 1 over 0. If you have 1 over 0, that is just equal to infinity. Take note, 1 over 0 is infinity. So therefore, to evaluate the limit of 1 plus 1 over x squared, we have 1 plus infinity. Therefore, the answer is infinity, using property number 1 from theorem 1.15. Next, let's find the limit of x squared plus 1 as x approaches 1 from the left. This is just equal to 2 using substitution method. Well, this one, the limit of cotangent of pi x as x approaches 1 from the left is equal to negative infinity. So if you are going to evaluate the limit of x squared plus 1 over cotangent pi x as x approaches 1 from the left, if this is given to be 2, so you have 2 in the numerator, while in the denominator you have negative infinity. So if you have a constant over infinity, either if it's positive or negative infinity, as long as it's infinity, the answer is 0. That is from property 3 of theorem 1.15. Now, if you're given limit of 3 as x approaches 0 from the right, which is equal to 3, and you know that the limit of cotangent x as x approaches 0 from the right is equal to positive infinity. So if you are to evaluate limit of 3 times cotangent x, you just have 3 times infinity, and that is equal to infinity. Lastly, if you have limit of x squared as x approaches 0 from the left, that is 0, and also the limit of 1 over x as x approaches 0 from the left is negative infinity. And therefore, if you are to evaluate the limit of x squared plus 1 over x, that is just equal to negative infinity, because you have here 0, limit of this is 0, and the limit of this is negative infinity. So you have 0 plus negative infinity is negative infinity.